Hi, Mike Collins here for Microlab. This is the first in a series of 2 videos that demonstrate the use of the Model 160 conductivity sensor. In this video we'll be doing a calibration. In a subsequent video we'll be using the conductivity sensor calibrated to monitor the course of a titration between acetic acid and sodium hydroxide. The assumption in this video is that you've looked at some of the other documentation that is available and that you're somewhat familiar with conductivity terms and with the Microlab software and the Microlab interface. Model 522 has a conductance jack on the front panel. The Model 160 conductivity sensor plugs into that. In order to use it, you have to remove the protective sleeve over the base of the sensor that protects the flow cell. The sensor can be used in conjunction with other sensors. In the next video, I'm going to show you how to use the sensor in conjunction with a thermistor probe to monitor the temperature and the drop counter in conjunction with the drop dispenser to monitor the course of the titration. For carrying out the calibration, you'll need conductivity standards. Now these can be made very readily and inexpensively in-house from dried sodium chloride and good quality deionized or distilled water. You can also purchase them from a variety of chemical suppliers. The ones shown are from Omega, and they are actually not all that precise. They are specified to plus or minus 2%. You can do better yourself. Notice the units though. The units that they specify on the label are in microsiemens. The actual units for conductivity standards are in microsiemens per centimeter. That's important. In the next video I'll be showing you the course of the titration. This is a setup that we'll be using. I'll come back to that in more detail in the next video, but I just wanted to show you down here at the bottom you can see the flow cell component of the conductivity cell itself. Make sure there are no bubbles in there. Now on to the video. I'm going to open the software, and I've got the latest version at the time of this video. You might check the Microlab website to see if there are versions later than 5.9.7. Those will be available for a free download. So the blue bar indicated that we're communicating fine with the Microlab interface. We're going to open a generic experiment. We'll leave it untitled. And we're just going to add the conductivity sensor. So we'll start in the upper left-hand window. We'll add a sensor. We'll go to the drop-down menu and choose conductivity. The next thing is to choose the input. We have to confirm that we have it plugged in to the conductance jack, and we're going to select 0 to 20,000 microsiemens for the range of the sensor. We're going to perform a new calibration, and again for this calibration I've got 4 commercial standards ranging from 45 microsiemens per centimeter to 4,500 microsiemens per centimeter. For precise work, excuse me, it's much better to have a smaller range with more samples over that smaller range, using just the range that you expect from your particular unknown solutions. The other thing to notice is the sensor units. We're going to use not microsiemens but microsiemens per centimeter. So let's perform that calibration. We're going to add a calibration point, and the first point we're going to use is with deionized water. So I'm going to put this on the stirrer, turn the stirrer on. I've got it set to some moderate value, and I'm going to lower the conductivity probe into the deionized water, and I'm going to check to make sure there are no bubbles. I've got all the bubbles out by jiggling it around. Deionized water at 25 degrees Celsius, which is the room temperature today, has a conductivity of 0.05 microsiemens, practically 0. I'm going to lower the sensitivity a little bit by dragging on the meter. We'll let this stabilize, and that's very good. We have our first data point. Let's add a next calibration point. And we're going to go from the most dilute to the most concentrated. So we'll remove the sensor from the deionized water. I'm going to wipe it off with a clean tissue. And then I'm going to use the 45 microsiemens per centimeter sample. Lower it in. Check for bubbles. There are none. And we'll just wait for that to stabilize. We'll type in the actual value of 45 microsiemens per centimeter. That looks pretty good. We have 2 data points. We'll add our third data point. Remove the 45 microsiemens sample, wipe it with a clean tissue, and now we're putting on 450 microsiemens. Check for bubbles, no bubbles. 450. Again, we'll lower the sensitivity. Now it seems like it's kind of wildly fluctuating, but actually we have the measured value in random arbitrary units are 33,000 plus or minus 10. So that is actually rock stable. We'll accept that. We're going to add another calibration point. So we'll wipe it down with a clean tissue. And we'll add the 1500 microsiemens per centimeter. We'll let that stabilize for a while. Check to make sure no bubbles. Okay, we'll accept that. Looks like a pretty good linear relationship. Let's add one more calibration point, most concentrated solution. Again, a clean tissue, wipe down the 1500 to get that all off. Lower it into the 4500. Check for bubbles. 4,500 microsiemens per centimeter. That looks pretty good. Okay. There we have it. We have actually 5 data points, counting the deionized water. We could try a first order fit, and we can see that that's not that bad, but it's not particularly great. Since we have 5 data points, we could actually try a second order fit that seems to be much better. Let's go back to the first order fit just for the sake of argument. With the first order fit, the slope of the line, which is your calibrated value in microsiemens per centimeter versus the actual sensor value, let's call that conductance, that ratio of y over x, the slope, is the cell constant. So the cell constant for this particular Microlab Model 160 sensor that I'm using is on the order of 1.36 per centimeter. Okay? Now again, if you wanted to get a better value, you would do the calibration over a much smaller range, no more than 2 orders of magnitude. But we have enough data points, why not? Let's just add a second order fit to it. We lose specific information about the nature of the cell constant, but we do have a good relationship between the microsiemens per centimeter and the measured value from the hardware, and we have an excellent correlation coefficient that way. So let's accept and save this calibration. The units are microsiemens per centimeter, and I'm going to call this, let's go in here with one that I did before, and we'll just change the date to today's date. And let's just mention that that is from 0 to 4,500, second order. There we have it. And finish. So let's do some measuring. Let's see how well that worked. I'm going to start again with the ionized water and work my way up through the standards after I wipe and rinse with another beaker of deionized water to get those salts off. So let's start with the ionized water and do some measurements, and then we'll finish it up. I'm going to click and drag the conductivity sensor. The deionized water sample is measuring 0.00 microsiemens per centimeter. Oh, I don't have it in yet. Here we go. Let's try this. No bubbles? No bubbles. Yes, it's still reading 0. I suppose it should read 0.05. But this is within the error of the hardware, the uncertainty of the hardware at 0 to 20,000 microsiemen range. Let's start with 45 and see what we get. There we are. So we're getting in the neighborhood, again, it's plus or minus 3 on the 0 to 20,000 range. So we're within what we would expect for that. Let's go to 450. Whoops, wipe it down first. There we go. 450 is measuring 465. $1,500 is measuring 1496, 1495. And 4,500 lastly. Measuring 4515. So again, this is a second order fit over an extremely wide range from 0 to 4,500 microsiemens per second. Actually, 3 orders of magnitude. Again, for the best results, it's recommended that you know what your range is going to be for your measurements and that you calibrate over that range. You get a much better fit and you get much better reproducibility. In the next video, I'll show you how to set up an experiment using the conductivity sensor. Thanks for watching.